Hello friends and welcome back to your channel GATEquestionsECE. I am back with next question on random variable and the question code is 107. If random variable z, x1 and x2 are related by z is equal to minimum among x1 and x2, then which of the following statement is true for the CDF of z? So we will have to find out which of the following is true for the CDF of z. What is the relation between the CDF of z and marginal or joint CDF of x1 and x2? We have done a similar question number 106, in which he has asked about the relation between z is equal to maximum among x1 and x2. So, proceeding on the similar lines of question number 106, we will see what is the solution of this problem. So, let's see the solution. To understand the solution, firstly we need to understand what is the CDF of x1 and CDF of x2. What does it mean graphically? So, we know the CDF of x1, we can represent it by this mathematical expression. So it is nothing but the probability that capital X1 is less than or equal to small x1. Suppose this point on x1 axis, this is x1 axis and this black line is x2 axis. Suppose this point on x1 axis, value of random variable capital X1 is small x1, and the line that is passing through this point is x1, small x1, and the line that is passing through this point, this line will be capital X1 is equal to small x1, and the region that is lying to the right of this line, this entire region is the region for which x1 is greater than small x1, and the region that is lying to the left of this line, this entire region that I have shaded here with red pen, in this region capital X1 is less than small x1. So according to this definition of CDF of x1, it is a probability that random variable x1 lies in this region, which includes this capital X1 is less than or equal to x1 region plus this boundary where x1 is equal to small x1. Similarly, we can see the CDF of x2. So it is the probability that x2 is less than or equal to small x2. So on this x2 axis, this is x2 axis. Suppose this point is small x2, and the line that is passing through this point, this line is capital X2 is equal to small x2, and the region that is lying below this line, this entire red shaded region, in this region x2 is less than small x2. So this probability will be equal to the probability that random variable capital X2 lies in this region, x2 is less than small x2, or on the boundary where x2 is equal to small x2. So that is the graphical meaning of the CDF of x2. Similarly, we can define the joint CDF of x1 and x2 graphically. So let's see the graphical meaning of joint CDF of x1 and x2. So this is x1 axis and this is x2 axis, and in this diagram I will explain the meaning of joint CDF of x1 and x2. So we can write the joint CDF of x1 and x2 by this mathematical expression. So this is nothing but the probability that x1 is less than or equal to small x1 and x2 is less than or equal to small x2. Suppose this point on x1 axis is x1, small x1, and the line that is passing through this point is capital X1 is equal to small x1. Similarly, on this x2 axis, suppose this point is small x2, and the line that is passing through this point will be capital X2 will be small x2, and the point of intersection of these two lines, the point of intersection will be x1 comma x2. You can note down here in the shaded region that x1 is less than small x1 and also x2 is less than small x2. So this probability will be equal to the probability that capital X1 and capital X2 lies in this region where they are less than small x2 and small x1 or on the boundary bounded by these two lines, capital X1 is equal to small x1 and capital X2 is equal to small x2. So we'll be using all these three definitions of CDF of x1, x2 and this joint CDF in explaining to find the CDF of z is equal to minimum x1 and x2. Suppose capital Z has some sample value small z, where small z can belong to any real number from minus infinity to plus infinity. So firstly, to find the CDF of capital Z, we need to understand what is this transformation. So we need to identify what are the points in x1, x2 plane for which minimum among x1 and x2 is equal to small z. So you can take all the points in x1 and x2 plane and check for each point what is the value of minimum x1 comma x2, and for after checking all the points in x1 x2 plane you will find out that only the points that are lying on this L-shaped boundary will satisfy this equation. All other points in the x1 x2 plane which are not lying on this L-shaped boundary will not satisfy this equation. So that was discussed in question number 102. I have discussed in question number 102 part 3 and part 4 video what does this transformation in x1 x2 plane looks like. So the conclusion in question number 102 was that minimum x1 comma x2 is equal to z is a L-shaped boundary with corner at small z comma small z. You can easily verify this. Here in this diagram I have drawn this L-shaped boundary with corner at z comma small z. So this point on x1 axis is z and this point on x2 axis is also small z, and this corner is z comma z. So this line is a section of line x1 is equal to small z, and this line is a section of the line x2 is equal to small z. So now to verify this, if you take any point on this L-shaped boundary, for example, if I consider this horizontal section of this L-shaped boundary and consider a point on it for this point here, then I can write the coordinates will be x1 comma x2, but x2 here everywhere on this section of the line is z. So the coordinates will look like x1 comma z. And also you note here that at this corner point x1 is z, but as you move to the right on this line x1 will increase. So it will increase from z, it will be greater than z as you move to the right. So we can say on this section x1 is always greater than z. So we can write here that on this section x1 is greater than z. So minimum among x1 comma z on this section of line will be z because x1 is greater than z. So everywhere on this line minimum among x1 comma x2 will be z. Similarly, you can check at this corner point that minimum among x1 comma x2 here will be z. Similarly, on this section, on this vertical section, you can take any point here. For example, if I consider this point and write its coordinates, then its coordinates will be z comma x2, and x2 is minimum here. Its minimum value is z, and as we move upwards its value will increase and will increase beyond z. So we can write that on this section, on this vertical section, x2 is going to be greater than z. So we can write that the minimum among x1, x2 for all the points here will be z. So for all the points lying on this L section, we can see that capital Z will be equal to small z. What is capital Z? It's minimum x1, x2. So minimum x1, x2 will be equal to z for this L-shaped boundary. Similarly, if you take all the points in this red region and find out minimum x1, x2, you will see that minimum x1, x2 will be less than z. So we can write minimum x1, x2 will be less than small z in this red region that is lying to the left of this L-shaped boundary. Similarly, for the region that is lying to the right of this L-shaped boundary, minimum x1, x2 will be greater than small z. So we can write this red region is nothing but capital Z is less than small z, and the region to the right of this boundary is capital Z is greater than small z, and this L-shaped boundary is capital Z is equal to small z. So the CDF of capital Z, we can write it as f capital Z small z will be equal to probability that capital Z lies in the region capital Z is less than equal to small z. Now if we observe the region capital Z less than equal to small z, you can clearly see from this that it is the union of two regions. One is that x1 is less than equal to z, and other is x2 is less than equal to small z. So this region that I have drawn here, it is a union of these two regions. So it is the union of these two regions. So we can write this probability will be equal to probability that x1 is less than equal to small z union x2 is less than equal to small z. So now we will apply probability A union B. So that is equal to probability of A, which is x1 is less than equal to small z, plus probability of B, which is probability x2 is less than equal to small z, minus probability A intersection B. So A intersection B means joint probability that x1 is less than equal to z and x2 is less than equal to z. So now we can write it as x2 is less than equal to z and x2 is less than equal to z. We know this probability is nothing but the CDF of x1 sample value z. This is the CDF of x2, and this is the joint CDF of x1 and x2. So we can write it as f x1 x2 z comma z. So that is the relation between the CDF of z and marginal and joint CDFs of x1 and x2. Also note, this is true even if x1 and x2 are dependent. So this is true even if x1 and x2 are dependent. So the correct answer to this question is option 4. So I hope you have learned in depth how to handle the maximum and the minimum among x1 and x2. So I hope you will like this video and press that like button and please do subscribe to my channel for more such videos in future. So thank you for watching this video.